Okay, for what we'll be looking into, we have from the 5th chapter, and we will continue working with row reduction among matrices. And for what we have at the start of this particular chapter, we have eigenvalues and eigenvectors. And we have, in the case of the definition for an eigenvector, and we have for a square matrix, okay, we have an eigenvector is going to be a non-zero vector x such that a times x is equal to lambda times x for some scalar lambda. And the value lambda, that particular scalar, is going to be what is referred to as an eigenvalue of the matrix A. If there is a non-trivial solution of x, of ax is equal to lambda x. And such an x is what is referred to as an eigenvector that corresponds to the eigenvalue lambda. And we have, just to get a little sampling, okay, you might have posed a question: if the vector u, which we have set equal to 2, 2, the question posed is this going to be an eigenvector of a is equal to negative 3, 3, 3, negative 3? And to test out, okay, we're looking at a times x, or in this particular case, we have x to be represented by u. And if I take a times u, okay, we have, in terms of matrix multiplication, have a 2 by 2 by 2 by 1. And in looking at what we have, now the product is going to be a 2 by 1 matrix, and looking at what we have here, so you have 2 times negative 3, 3, plus 2 times 3, negative 3, and for what we have in the product of the top row and bottom row elements, okay, we end up with 0, 0. And again, for an eigenvector, okay, it should be non-zero. And for what we have here for the result in the product for a times u, this comes out equal to 0. And we have from this, on the basis that the product is 0, we cannot say that u is going to be an eigenvector of this particular matrix A. And another situation, say if you have vector v equal to negative 3, 2, and we're asked if this is going to be an eigenvector of a is equal to 1, 12, 6, 2. And so looking at representing a times x, we have a times v. And so taking the product, okay, so we have negative 3 times 1, 6, and we have plus 2 times 12, 2. And we have negative 3 plus 24 is 21. And for the bottom, we have negative 18 plus 4 comes out to negative 14. And so we have 21, negative 14. And this is going to be a scalar multiple of negative 3, 2. In fact, 21 is negative 7 times negative 3, and negative 14 is negative 7 times 2. So we can say that for the product, this comes out to negative 7 times u. So since this is a non-zero vector, okay, now v is going to be an eigenvector. And for that coefficient, negative 7, okay, that will represent our lambda, or in this case, our eigenvalue. So we have, so v, negative 3, 2 is going to be an eigenvector, and this will be an eigenvector that corresponds to the eigenvalue which we have at negative 7. Now, we have, for this particular matrix A, all right, we have negative 7 is an eigenvalue. But let's say that supposedly 10 is going to be another eigenvalue in its own right. And we have showing that along with negative 7, that 10 is also going to be an eigenvalue of the same coefficient matrix A. So in looking at testing out, okay, so we have a times x is equal to lambda times x. And if I combine x terms, have a minus lambda times x is equal to 0. And now considering that I refers to an identity, we can say that a minus lambda can be rewritten as a minus lambda times I. And for what we have in the setup, okay, now we have a minus lambda I quantity times x is equal to 0. And if I were to take the determination of a minus lambda I, which in this case setting lambda equal to 10, we have a minus 10I. And so looking at what we have for the corresponding parts, now remember I would be 1, 0, 0, 1 for a 2 by 2 matrix. and 10 times that we have 10, 0, 0, 10, and taking this and deducting from the matrix A, and for what we have in the corresponding parts, okay, we come out to the 2 by 2 difference at negative 9, 12, 6, negative 8. And it says that to find x, it says to set what we have for this difference times x equal to 0. And so for what we have in the scheme of things, okay, so we have this 2 by 2, and we have x represented by x of 1, x of 2 equal to 0, and formatting for what we have as we have done in prior sections as an augmented matrix. So we have negative 9, 12, 0, 6, negative 8, 0, and if I were to reduce, okay, put this in reduced echelon form, I would have one negative, or I should say reduced row echelon form, or reduced echelon form. So I have 1 negative 4/3, 0, and again I have 0, 0, 0, and here we're going to have in this case a non-trivial solution, and we have just for the setup we have x of 1 is equal to 4/3 of x of 2. X of 2 is a free variable, and for what we have for x, we have x of 2 times 4/3 and 1. And so for what we have in effect, okay, so lambda equals 10 is going to be an eigenvalue, and we have each vector of this form with x of 2 not equal to 0 is going to be an eigenvector that corresponds to lambda is equal to 10. And we will be looking into eigenspaces in just a moment.